So what I'm going to show you now is some of the more technical aspects of what happens under the hood when you create a new filter. Within this scene we have a moving object and a moving camera, and I just want to show you what happens when a filter is actually built. You can see here some of the modules that are used to construct the node networks that we're going to be using. The important thing to note is that everything that this tool does uses mostly vanilla Maya nodes, with the exception of a single node, which is the actual time filter node, the heart of the operation. This node has to update on the fly, so it has to take user input and regenerate time data on request. So that had to be created using a custom node, but everything else is vanilla Maya and a lot of trial and error. So let's go ahead and create a new drop frame filter with a hold of 2, and what I'm going to do is open up the node editor so you can see what's happening when we create this. So let's create that and see from the node editor point of view. Now what's just been made here, we have the control object here, a bunch of stuff which I'm going to describe soon, and we have finally what gets output. So we can see we have a bunch of networks made here. If we graph the output of the actual filter, we can see there's 2 distinct chains. The first chain over here is creating something called the CamWas object, and every time filter has one of these. If we check the outliner, which is here, we can see that there's a CamWas object which is invisible. And if I make that visible, we can see what that is. It's just a locator which tells you where the camera was at a given point. Now this time filter is on 2s, so that means that this object will hold on 2s, and that will change in any way that we change the actual filter. So if we say hold on 4s instead, then we'll see that that CamWas object will stick around for 4 frames, then jump to the camera. It tells you where the camera was. I'm going to delete that key for now. As of this moment, this locator does nothing to our animated object. If we go to our camera here, we can see that the object is stuttering in the viewport. It's not holding still because we haven't time filters don't by default have a camera offset attached. What they do have is just the entry point for what the camera offset is going to be, and that camera offset is here. This guy here is the entry point for that. If any of this looks complicated, it's because it is. It took a lot of trial and error to figure out how all this stuff was going to work, but I'm going to get into that very shortly, starting with how is the CamWas node created. So the CamWas node is the simpler of the 2 setups. You can see in here what happens. We have a camera, which is your user camera. We have Maya time going into the time filter node, which puts out manipulated time, whether it's a time warp or a drop frame filter. The manipulated time goes out. And then what we have to do is split up the camera's transformations into translate, quaternion, rotate, and scale. The reason we use quaternion is that we found that when we were manipulating time using different methods, the only way you could get accurate results is if you're querying quaternion. You can't use just translate XYZ. That doesn't work for all cases. So we split apart the different transforms using 10 frame cache nodes, and a Maya frame cache nodes basically takes a data stream and queries the value at a given time. So that's what's happening. You can see it's pretty much exactly what's going on here. We have a time to unit, which is the time we're querying, the decomposition node, which takes the quaternion, scale, and translate. 10 of these frame cache nodes. Now, I don't know if it's possible to do this with a single node. In new versions of Maya, when we built the tool, this was the only way to do it, so that's what we did. The results get recomposed in a 4x4 matrix. That gets decomposed, and the translate, rotate, and scale go out into the CamWas node, and that's what we have right here. So, and as the camera moves around, so too does the CamWas node. So we need that. We need to know where the camera was, because that is the space we're going to be multiplying through our camera offset matrix. So let's go back to our camera view, and let's just kind of change what we've done here so we can see our target object. Alright, so we can see that our target object is stuttering around in space, and we want to fix that. How are we going to fix that? Well, we're going to add this guy to a camera offset node, camera offset network. I'm going to open up the graph here so we can see what's actually happening. So let's go ahead and create a camera offset network. Now what you can see here is what happens as we output. We are creating kind of a string of matrix multipliers, and this was the part that took the longest to figure out, is how to express camera space based on a given time and pipe that through to the objects or the object or objects in question. I'm going to go in detail and show you how we figured this out. So what you basically see here is a string of math. We have multi-offset, we have object to world, we have world to camera, and finally camera to object. There are 4 multiplications that are taking place to specify the space that happens. Again, if we look from the camera, now you can see that our target object appears to stay still as we're doing our time filter. Yeah, figuring that part out was quite tricky. So what's happening inside of this node is, the first thing that happens when you create a camera offset is we need to make a duplicate matrix of where your offset node is going to be. You can't use the offset node itself because that creates a cyclical dependency, and that doesn't work. So the first thing that happens is we create this storage node, which either takes the static transform or the animation of your original node, because this thing must support offset nodes that are already animated. So anyways, this is basically, this guy here is a duplicate of your original node. The first thing that happens is we take this duplicate node and we multiply it by the node parent matrix, which basically gives you a duplicate matrix of what your original node is. You need that. The next thing you do is we have our CamWAS object here. Its world inverse matrix, you multiply our duplicate matrix by the world inverse matrix. The sum of that gets multiplied by your camera world matrix, and the sum of that gets multiplied by the parent inverse matrix of your original offset node. Finally, that goes into a switch, which allows you to either, that switch is the result matrix or the original matrix, which allows you to turn the effect on or off, and that gets piped into a decomposed matrix, which pipes back into the node parent matrix. Again, a lot of trial and error to get this working, but that you can see here is the composed matrix, which is a duplicate, a storage node. This guy, yeah, there's a lot of back and forth here. There's a lot of back and forth before we get to the actual math. We can see here the parent matrix into that, the CamWAS world inverse matrix into this, your actual scene camera into this. This is a choice network because, again, you have the option to choose different cameras within the scene. And then finally, that gets multiplied by the parent inverse matrix of your original storage node. And that's the basic setup, the basic math. For those of you who are familiar with matrix math or working with matrices in Maya, we'll have some sort of breadcrumb trail for how to replicate these results. But the point is that from a different camera, the motion looks kind of strange, but from your camera, it looks exactly like what you would want it to look like. And the addition of switch and blend nodes allow you to actually change the result. I can just grab this object here, change the result from different cameras. So if I want it to work from perspective, now it's working from the perspective camera. Or stick it back to camera, now it's working from camera. So that these two things were this is where the most R&D went into, to figure out how to get the CamWAS node working, how to do the matrix math to actually have this functional. The other difficult part was how to publish this data to the pipeline, how to build this and then reconstruct it later on down the pipe. And the pipeline stuff is very studio independent, so that's something I'm not going to get into right now. But in short, an entire new class of data had to be registered for an animated project, because this object exists kind of outside of the typical scope of things that are normally published within the pipeline.